So, welcome to Tuesday. Welcome to Homework 4. But before we get started with Homework 4, are there any questions so far about Homeworks 1 to 3? Any class procedure questions? Anything like that that we should discuss before we jump into the homework itself?
Are we gonna have any kind of like review before the exam?
Um, Not really, no. The kind of. So only in the most useless sense possible. Next Tuesday, I am not available for class, so I will not be here. Um, you guys can do whatever you want, but it wouldn't be an unreasonable use of your time to talk amongst yourself and review amongst yourself for the exam. Um, the exam is going to be exactly like your homework in the sense of it will be a combination of the easiest problems you've seen in your homework together with the easiest problems you've seen in your homework written in a strange, weird way that made it not completely obvious it was one of the easier problems from your homework. So what usually happens on the exams are students look at a question, go, oh yeah, I know that. That's just for my homework, and write it down immediately. Go to the next question. Oh yeah, I know that. And write it down immediately. Go to the next question. Go, I have no idea what you're talking about. And that is not the infrequent sort of view of the exams. So the best way to review for the exam is to make sure you have thoroughly understood every homework problem. To the extent that not necessarily that you've memorized or even are very good at getting every step of the derivation right, but that you've understood why every problem was set up the way it was and how setting up the problem that way got you to the answer you needed to get to. And if you understand at that level, you will probably find the exam super easy. So that is going through your homework and making sure you've understood why everything is correct. Not what the answer is necessarily, but why the answer is that. And you will either find the exam super easy, or you'll find most of the questions easy, and a few of them were just weird, tricky, and I gotcha, which is no big deal. Other questions? I'm not exactly sure when the exam is. I think it's a couple weeks from Thursday or so. Is that when it's on the schedule
The
for?
syllabus says March 18th.
Yeah, that sounds about right to me.
I had a question about what homeworks will be on it. Is it just, I see that homeworks 1 through 6 are due prior. Are those just the ones that are going to be on it?
And you'll probably imagine that the vast majority of it will come from, 1 through 4, 5, like we're going to change gears when we get, I think it's the next homework. I think it's homework 5, we'll start doing selection. And so you might imagine the vast majority of the exam will be pre-selection, and in a little bit, we'll have a few results from natural selection in there. But it would be, it'll be at the very worst proportional to the home, if it's 6 homeworks, you imagine 2/3 of them are going to come from 1 to 4.
I think also in the first week you mentioned something about creating a cheat sheet. Did you want us to then submit that to you?
Yep.
Okay.
So the best way to study for the exam, honestly, is to understand why all the homework is correct. And the last thing on earth I want any of you to do is to memorize a formula you can look up. That is a stupid waste of your time. So, but if it is simply an observation that if I tell you the exam is open book, there is some fraction of you that will not study in any way and just assume you can pull it off at the time of. And that's a bit of a disservice. So I make you write down a sheet of paper that has on it every formula you want to use on the exam. And and normally I would just like glance at it in class, but since this is going to be a take-home exam, I'm going to ask you to send me your sheet of paper before I send you the exam, so that you write down all the formula you're going to use and send it to me. And I have traditionally said a sheet of paper because I don't want it to be I don't want you to spend months making it. You probably don't need that much on it. There aren't that many formula, if you know what I mean. But we'll see how this works. So send me something that is your list of formula before the exam, and then I send you the exam. And I'm going to ask that you try to keep your books and your videos and your PDFs closed during the exam. It won't matter too much, but I will ask that you try to. And we are adults here. I will be surprised if I go to any effort to police this exam in any way. I don't want to. I don't want to need to, if you know what I mean. I want you guys to do your best, and your best will either get you a B, or if you're great at this, it'll get you an A. And I don't think we should care much either way. Does that make sense? And I'm dead serious. Do your best. You'll get a B, no matter what your best is. And if you're any good, you'll get an A. And don't sweat it otherwise. Other questions? Okay. With this in mind, let's get started on homework number 4. We're going to begin with problem 1 in Linnea. She's here, isn't she? Yeah, there we go.
Sorry, one second.
Yeah. Have I remembered to allow you to share the screen, or did I forget again, as always? Find out.
Okay, sorry, one second. No, I just put it on here a second ago, so. Oh, there we go, okay. There we go, okay. All the way up to the top. Okay, all right, number 1. So I kind of thought that this was, I thought this basically last question from the previous homework. We're basically asking if we have an allele that's at a certain frequency, what's the probability of it being fixed or being lost? And we already learned that the probability of fixing an allele is just the frequency that we have initially. And there's only 2 eventual probabilities, either it will be fixed or will be lost. And I realized I didn't actually write the probability of being lost, but the probability it will be fixed is its current frequency. Sorry, it's actually I'm on the West Coast, so I'm always a little tired.
Oh my.
But yep, and then I didn't put the probability of loss, but it would just be 1 minus 12, so the 88%.
Exactly. This problem is here just to make sure you did understand the last problem of the previous homework. And honestly, this is as useful and important and as deep a result if you're an evolutionary biologist as you're going to get out of this class. To always and forever remember the chance of an allele fixing is its current frequency will be an intuition if you do any kind of like evolutionary biology, evolutionary genetics, that will help you the rest of your career. And It's dumb. It's dumb that I asked you to repeat it again and again, but it is simply because if you don't forget it, you will find various times the rest of your life you're using it happily. So keep it in your pocket.
Since it's important, can I show? I wrote out the logic for this one. Can I show and make sure that I'm not crazy?
Absolutely.
So how I set it up was like the probability that the proportion is 1, or the frequency is 1, given that the initial frequency was 0.12 is what it says. And then I turned that into the actual counts. So the count of x equals 2n, given that x started at I, equals this. So then I just crossed out the 2 n's because we knew the frequency. So it's just the frequency. Is that correct?
That's the count the expected count will stay the same. The expected frequency will stay the same. So there you go. If assuming, and all of this does assume, that the population size stays the same, 2n. So if the population size is varying, we can actually prove this is true too. Nothing about this will actually, the population size varying will not affect this proof, but we've probably used the fact that it doesn't vary as part of it so far. So I'm sure we could generalize if we needed to.
Question about this one. So on the previous homework, we were asked this question, we were assuming no mutation.
Yep.
In this problem, we're not assuming mutation. So this holds in the event of any kind of mutation, right?
So in the event of a mutation, none of this is particularly true. So if there is one-way mutation, if there's mutation away from the allele you're looking at to something new, your intuition is going to be that eventually it'll be gone. Eventually it shall mutate away and there'll be no copies of it. If there are two-way mutation, there's a mutation to the allele and a mutation rate away from the allele, I bet you can solve that problem pretty quickly. And you'll probably end up proving that the equilibrium frequency of the mutation is something like the ratio of the two mutation rates, where the numerator is the rate to the allele and the denominator is the total mutation rate to and from the allele. It will turn out that when there is mutation in both directions, and a population size is relatively large, n doesn't matter in any way. It ends up being sort of dominated by mutation. But I don't think we're going to prove those results in this class, but they would be, I think they'll be straightforward to you. You can very well prove them in a similar manner by writing down the change in allele frequency under your mutation model, constructing a martingale, and or not, and your first stochastic processes results will probably lead you home to the equilibrium frequencies.
Just out of curiosity, if one of the assumptions you said was that we're assuming that the population size doesn't change.
Yeah.
How would you approach it if it does change?
Well, you just allow the population size to be a random variable, and then you integrate over the distribution of that random variable, and you'll find that it just falls out of the equations very quickly. That it will be very much like the problem that the first couple problems we did where we were like integrating over the distribution of the allele frequencies next generation. Here you'll be integrating over the distribution of population size next generation. And you're going to end up with a result that is very rapidly looks like it doesn't matter for mean effects. For variances, it'll matter a lot. It'll matter how fast it goes away. It'll matter for that sort of stuff. But for mean effects, it won't.
Okay.
Other questions? So up next with problem 2 is Carmen.
All right. So I actually just realized that I had a mistake on this one. So it's off by a factor of 100, but basically I solved for the like R terms, and that 100 in the denominator should be 1 over 100.
Let me see, what do you got there? Pulling up my answer too. So we got the probability. I've already forgotten what the problem is. I'm sorry, let me, can you get the problem? What was the problem? So the problem was at 99.99% of the time, it's at a big number, and 1 in 10,000, it's at a little number. Okay, and we're trying to find the harmonic mean. So in your, we have with probability 99.9, it's at a very big number. At probability 1 in 10,000, it's at a little number. And yes, that 100 is supposed to be 1 over 100. Absolutely. But otherwise, that is absolutely correct. This is that is nothing more than a typo. It should read 1 over 100, much like it reads 1 over 10 to the 11th. And if it read 1 over 100, I think we probably would have gotten something very close to 1 million for the effective population size, rather than 100. Does this make sense? Is everybody on board with this? Did everybody get something close to 1 million when I plugged in? Any questions? This is absolutely right. The harmonic mean of something is is 1 over the expectation of 1 over that random variable. So the harmonic mean of population size is the expectation of 1 over the population size, over the distribution of population sizes. This is really, really weird why I'm doing this and why we're going to do this for like 6 problems in a row for no apparent reason other than it's going to be part of a biological explanation. And I wanted first us to get comfortable with the idea of a harmonic mean, so that when we start saying things that sound at first blush stupid, they're actually really sort of very clever explanations. So up next with problem 3 is Brooke.
All right, 1 second.
Getting to this, yes.
Okay. All right, let me just scroll. Oh, we're at 13. We're gonna go take a journey. Okay, so the question was, for a fluctuating population, how many years will it take to exceed 1 billion, basically, was the question. So the way I approached it was just knowing—
Biologist, look at this.
I guess.
Growth.
Yeah, so I think what I knew was I wanted to know how many cycles it was going to take to double. So that's solving for x, basically to exceed the number 10 to the 9th. So just breaking that down, to solve for an exponent, you can take the log of the numbers to bring down the exponents. And that basically brings me a more precise number, which was 29.89. I think if you want to round it down to 29, it's a little bit of a smaller number of years. But you know that each cycle is 5 years, so you also want to multiply by 5 to get the number of years.
Yes. So this is very, very much thinking like an ecologist, because you've assumed growth is perfectly continuous, and there will be 149 years, 149.45 years. That is exactly correct, because that's the way biology works, is continuous growth. The stupid problem said it was an instantaneous jump, so it would be 30 cycles.
Okay.
Because the problem is made by an idiot who doubles population instantaneously. Doesn't work like a biologist. But in any biological system where you had continuous growth at that constant rate, that would be the exact correct answer, rather than the silly artificial rate that I created for the problem. Does that make sense to everybody? So I created a silly problem with 30 cycles that approximated a biological growth of 149 years.
I have a question. I think the population starts from 2 instead of 1. So should it be like 145 years?
Yeah, if it does, it will be one less cycle. Yes, if it is written in such a way that we are currently at size 2 rather than size 1. This is the answer for how long it took to. Well, anyway, if it started at size 2, it'll be 29 cycles, and if it started at size 1, it'll be 30 cycles. I'll just put it that way. And
Yeah, it did start at 2 cycles. You're right.
none of this matters. Sorry. Let me get rid of this. I think someone's offering me an extended warranty on my car. Sorry for that inconvenience, but yes, that is almost however you've interpreted the problem is of no great consequence. The idea is in the end of these 7 or 8 silly problems, we want to see what happens when a population is constantly growing and constantly declining. What is the harmonic mean population size versus anything else which we might find a more intuitive measure of size, like the expectation or normal average. And if you interpret this as taking 31 cycles rather than 30, if you interpret the problem as because I don't really care exactly what distribution you put on population size. I really just care that you have a distribution that has the property that it spends a little time in every size. We're going to see what that does to harmonic mean. And if you are a factor of 2 off of your colleague, do not worry. It's not going to change our intuition. I think if you construct it exactly the way I constructed it, the math will be a little easier than some of the other natural ways of reading the problem. Okay. Up next is Zhangji with problem. Where are we? 3, 4? Oh, I've already lost myself.
4.
4. Oh yeah, this is.
I think I'm sharing my screen now.
Yep.
So, okay. And I think I'm also giving away problems 5, 6, and 7.
Yeah, probably there's a good chance of it.
All right. Anyways, so problem 4 so problem 4 says that if this population exceeds 1 billion, it stays there for 5 years and then shrinks, and then it goes through the cycle every 5 years where it doubles or halves, and what fraction of the time is this population at size 1, 2, 4, and so on. So I guess if I can just explain this instead of reading my reasoning. So if we imagine the population is going around a cycle, then at size 1, every time it reaches size 1, it would have visited the other, I guess, 28 generations in between twice. And then the last generation is generation 30, where it exceeds 1 billion. So generation 1 and generation 30 would have been visited once every time the population, I guess, goes through the other generations. So there are 30 generations, and so there's, for the time it spends at generation, I guess, size 1 and size more than 1 billion is 1/30. Sorry, the time it spends at size 1 and size more than 1 billion is let me get this correct, because I don't want to mess up, is 5/300. So 5/300 is 1/60. Okay. And then the time it spends at generation 2 to 29 is 10/300. So that's 1/30. Okay.
Yeah. This is exactly how I intended the problem to be read. And
Okay.
and If you read it slightly differently than this, this is how I intended it to be, how I intended these words to be read. And I've taught this this problem enough times to enough students that I know enough of you will misread it, or at least read it with a meaning very slightly different than this, that I do not care. But this is the exact intent I had in the reading. And this was the exact logic I had when I solved the problem, that it spends exactly 5 out of 300 years, or 1/60th at the top and bottom sizes, and it spends 10 out of 3 years, 1 out of 30, and all the in-between sizes. But reasonable people might have misinterpreted whether we spent 10 years at the bottom or 10 years at the top, or be almost one off on our counts sometimes, but we're not going to fight about that. Is everybody clear on this? And again, the importance of this is not that you wrote down these probabilities to be the exact same probabilities I wrote down, or Zhangxi wrote down. It is, we will see in a second what the mean population size is, what the variance in population size is, and those will be, I think, intuitive to you, given that the actual sizes are really large and really small. But the harmonic mean will be not intuitive to most of you until you've started doing these kinds of problems. So up next with problem 5 is mega.
Okay, can everyone see?
Yeah.
That bigger. So for 5, you literally just put it into the mean formula. And so you have the probability that it's at 1 and the probability when it's at max, plus the probability of all the in-betweens. And then you said to look up how to find the sum of a geometric sequence for the second part because it's increasing. So I did that.
Yeah.
And then this is just the math, and I got 5.3 to the 7th, which is like 53 million.
That is exactly what I got too. Did anybody get any? So first off, this all makes sense to you, right? That the expected size is just the probability of the size times that value, summed over all potential sizes. We might as well be on week 1 again. And from that moment onward, this is nothing but arithmetic. And but it turns out there's a slick formula for the arithmetic when you have a geometric series, where you have a series where you have a number, and then the next number is the first one multiplied by something, and the next one is that one multiplied by something, and you add them together. That's a geometric series. It is a number, and you multiply it by something, and then sum them all up. And that has a very cute looking formula that is in terms of the first value. R is in terms of the ratio between successive values, and N is the number of terms. And you get something like this. And if your calculator doesn't screw up or you don't mistype it, you end up with 53 million or so. Does that make sense to everybody? So we got a population that is sometimes 1 billion, sometimes 2, sometimes every value in between. And the expected value, the arithmetic mean value, is somewhere in between, like 53 million. Doesn't seem hardly surprising at all. If it gets up to 1 billion, gets down to 2, maybe the mean is somewhere, if not exactly halfway in between, at least not so dramatically different than halfway in between that we're confused. Does this make sense? Okay, up next with the variance is Michelle. Is she with us? No Michelle today? She's sick. She might have told me already. I can't remember. Up next is Sebastian with the variance.
Okay, just give me a second. Can you see my screen?
Yeah.
Okay, so I wanted to show you something from the previous problem, is that like for the summation, I didn't want to deal with that with the formula mega use, so I just made two vectors in R and carry it as summation.
Man. I've got a tool. You're a smart man. You said, I have a tool to do summations for me. It's called R. Why should I memorize a stupid formula when I can just plug the damn R like an adult? Okay.
Yeah, I was just thinking everything as like a conveyor, like two conveyor belts going together. I was like, oh, what? Like that's two vectors, and then let's just do it this way. It's just fun.
Yeah.
And for this one, the variance was like a really, really big number. So I just plugged in the values to the formula we had. So, okay, so the variance is here. And for this, I needed to calculate this bit here. And I don't know if my answer is okay, but well, I also use R for this bit.
So the only thing to say is your formula for the variance has a plus where it meant to have a minus. It's the expectation of n squared minus
the
expectation of
okay.
So so there should be a minus there, but the idea of the expectation of n squared is a number that looks like 10 to the 16th. The expectation of n quantity squared is a number that looks like, oh, again, something on the order of 10 to the 15th or 10 to the 16th. And the variance looks like another number that is on the order of 10 to the 16th is entirely correct. And a bit intuitive. I'll pop up my screen to get up the exact numbers. Let's see. No, that's text. There it is. No. Let's try again. Someday I'll get good at this. I know I will. But it's not going to happen anytime soon. Where is Zoom now? Let's try this one last time. I can do this. There we go. So when I do this problem, it is set up exactly the same. Oh, wait a minute, which problem are we on here? Here we go. So it is set up the exact same way you set it up. I started out with the expectation of n squared. I wrote that out as 1/60th times some numbers squared, 1/30th times some numbers squared. That became a summation. I didn't use R. I actually plugged in the silly formula, and I ended up with a number that looked like 3.2 times 10 to the 16th, which might be a little bit bigger than the number you had there. My guess is if there's a difference, it's in the number of terms or something. I might have and then when I do the subtraction, I end up with something closer to like 2.9 times 10 to the 16th. But all of you should know how to set this up. It is the expectation of n squared, which are probabilities, times the value times the size of the population squared, summed over all probabilities and all sort of values. Probability times value squared, probability times value squared, probability times value squared, etc. I've just pulled out my probabilities to make these sums look neater. And then you can do it in R, you can do it in Excel, you can do it on a calculator, you can memorize a formula, but it doesn't really matter. Once you've set it up, you've got it correct. And the answer turned out to be a whopping, huge, ridiculous number. And this should be one of your deep intuitions also. When you have a random variable and it takes on some set of values, the variance tends to look like the larger values it takes on squared. Not exactly the biggest value squared, but closer to the biggest value squared than say the smaller values. So if this thing goes up to 1 billion, 10 to the 9th, you're going to be expecting that variance to be somewhere in the range of 10 to the 18th. That's your intuition. And in this particular case, it's a little smaller because it spends a bunch of time at small values too, but it's still a huge number. It's a number like 10 to the 16th. So variances tend to look like the square of the observed values, and means tend to look like the observed values themselves. Variances are on a scale squared, means are on the sort of scale of your values. Oh, and of course, variances by definition, because they're the sum of things squared, have to be positive. So when sanity checking the rest of your results, the rest of your life, make it be like this. If I got a whole bunch of values, the mean ought to look like something like the middle of them. And the variance ought to look like that squared, something like that. If you're way off orders of magnitude, chances are something went a little funky in your calculations. It's just a sort of sanity-ish check. Questions? All right, Young Song, can you do the harmonic mean, problem 7? I think you might be muted still. Are you? I see beautiful.
Can you?
There you go. That's it.
Okay. So I already knew that I messed up with the harmonic mean. So like I try to sum like add the reciprocals and then make it a reciprocals again, but then like this 1/30 shouldn't be here. It should be outside of the denominator, and that will result in a different answer than this one. Yeah.
It probably will get a number very slightly different, but so from the first moment when you've set it up, this you've got slightly different probabilities than I did. I ended up with a 1/60 for the first one, and a 1/60 for the last one, and 1/30s for all the rest. But I don't really care. But so far, this is just absolutely perfect. It is the harmonic mean is 1 over the expectation of 1/n. So the probability times 1/n plus the probability times 1/n plus the probability 1/n. This is the exact right setup with very slightly different probabilities at the edges. And from there, it's really nothing but just a silly little bit of algebra. And when I do the silly little bit of algebra, I got 1/60 times 1 plus 1/60 times that number plus 1/30 times 2 to the minus I. And then I've got another geometric series. I probably just plugged in the result. And I might have substituted this is a small number. I may have done a slight approximation there. But anyway, I got about 1/20 as the harmonic mean. I mean, as the expectation of 1/n. So the harmonic mean I came up with it is 20. Is that what you guys did? Anybody get a value dramatically different from 20?
29.7.
Yeah, okay.
It's 19.22 different.
Yeah. I may have approximated this a little too much, to be honest with you.
Okay.
That looks like it really should be I probably should have kept that entire sum.
So I don't know if I really did it 100% correct, but I kind of feel like I might have did a shortcut cheat way, just by like intuiting that this was a geometric distribution, and knowing that the harmonic mean of a geometric distribution is 1 over the probability. And then just understanding that the probabilities are basically, if you have p times x, it's 1 over 60 and then 1 over 30. And so if you do the sum of those two probabilities together, you're going to get 3 over 60, which is 1 over 20. And then you invert that to get you. I don't know if that's really the right way to think about it, but
it's not a terrible way to think about it. And the difference, right, is so it's these sums don't go to infinity. And although my approximation might have sent it to infinity. But that intuition is more or less correct, right? That geometric sums and geometric series are fundamentally deeply related, and that you can think of a geometric sum in terms of a geometric series, or even think of expectations of geometric distributions as being derivable from geometric sums, and they are all as deeply related as you think, and that you ought to be able to relate them in some fashion or another is just correct. You know, for here I wanted you to do nothing more than just plug in values, but you know, there we go.
Can I ask a question about the limits on the sum?
Yeah.
So why do we have 2 to the 2 to start with? Wouldn't we also need to have 2 to the 1? Because wouldn't we expect the population to go 1, 2, 4, 8?
I have my 1 right there.
Right, but wouldn't there be a time when the population is size 2?
Oh, you're saying this sum should go from 1 to 29. That 2
Yeah.
is a typo. Yes.
Oh, okay.
You're
Gotcha.
correct. That 2 there is a typo. It should be I equals 1 to 29. You are absolutely correct. And if, yep, no, but yeah, that sum is basically 1. Anyway. Anybody else want to talk about this one? Whether you got the number 20, whether you got the number 30, whether you got the number 50, whether you got the number 60, whatever. The answer is you got something you can count on your hands. This population starts at size 1, goes to 1 billion, comes back down again, spends most of its time like in the thousands and millions. Really, really big numbers. The mean is 53 million. The variance is 10 to the 16th. The harmonic mean is like something on your fingers. It's like 10 or 20 or 30 or something. It's a tiny little number. And we'll talk about it a little more once we derive some things with theta. But the reason we want this intuition about harmonic means being very, very small is because when we derive stuff about variation and about the probability 2 alleles are the same or different, we're going to end up with formula that look like 1 over 1 plus 4n times mu. But the way n appears in them is in the denominator. So the heterozygosity that matters, the n that matters for heterozygosity, if that's what we're trying to understand, will turn out not to be the total population size, not to be the the arithmetic mean population size, but it'll be proportional to the harmonic mean size, because in every formula where you see the n, it comes up as a 1 over n term. And the intuition will be, if you're trying to estimate or understand heterozygosity or homozygosity, the intuitive quantity that you're going to have to wrap your head around is the expectation of 1 over n, not the expected size of n itself. That means most organisms, like humans, that you're perfectly well aware of, have like, I don't know, how many humans? 7 billion of us maybe now. You might have expected human heterozygosity to be a function of a number involving 7 billion. Human heterozygosity is a function of a number involving 10,000, maybe 50,000. And the intuition is going to be the effective size of humans is something on the order of 10,000 or 50,000, because probably human population size hasn't historically been 7 billion. Historically, it's been closer to maybe 10,000, or at least it has spent enough time at values close to 10,000 that the harmonic mean is there. And we'll talk about this a little more as we move along. But is this clear so far to everybody? So I'm having you calculate these harmonic mean sizes, not because I care about them, but because you guys are going to need to see how these things work to have the intuition that heterozygosity isn't always wrong, or at least it might not be. Or at
So
least,
is that, I guess, saying that the effective population size is more likely to be the harmonic mean than the normal mean of the population? Okay.
you can in fact prove it. You can in fact prove that if nothing is going on other than mutation and drift. I don't think we do the proof in the book. Maybe we don't do it as part of this class, and I'm not sure if we do it in the book or not. But you can actually prove that if the only thing going on is mutation and drift, the effective population size is approximately the harmonic mean size, if it's not exactly the harmonic mean size. But even without that proof, it should be intuitive to you, because you're going to see that damn 1 over 4n over and over and over again until you're sick of it. So the intuition that what is going to end up mattering is 1 over the population size average more than the average size is, we're going to build that intuition the rest of this class, the rest of this homework. So the number of times you see that. Problem next, problem 8, we have Taylor.
No. Okay. So let's see, problem 8 was 2.10 in Gillespie's book. So we have, if the human generation time is 20 years, what effective population size for humans is implied by the data? So we're given a mutation rate on the scale of a year. So first of all, they calculated a U to be 1.44 times -7.
I'm sorry, I didn't quite hear. What did you just say? I missed it.
So when they were
Well, you're cutting out. I'm sorry, I lost your audio. I know you're saying interesting things, but I can't hear you. I'm sorry, Taylor. You are just gone. Can anybody else hear? No. No.
Frozen.
Up there, you're back. Are you back?
Can you hear me?
Yep. Oh, we could. Oh, gone again. All right. I'll talk through it for you. Or maybe you were going to say something very different. But you have here, that because it's going to mimic very much what I have, that the mutation rate per year is 10 to the minus 7th, and that a generation per year in the generation time is 20 years. So a mutation rate per generation is approximately the mutation rate per year times the number of years in a generation, giving us 2 times, here, now I'll share my screen. Where's my screen? Giving us 2 times 10 to the minus 6th as the mutation rate. And here I used a very slightly different approximation than Taylor did. I used the full-on H at equilibrium equals theta over 1 plus theta, which gives theta is equal to H over 1 minus H, which can very reasonably be approximated just by H for anything other than, for certainly when H is small. This is very well approximated by simply H itself. And the problem, or the data somewhere referenced in the problem, suggests that that heterozygosity is on the order of 0.1. So I got 4n is equal to 1/9 over, anyway. You get a number, in the end, you get a number that says n is equal to 12,500 if you assumed theta was approximately equal to H, or you get n is equal to about 13,000 if you were if you use the full on H hat equals theta over 1 plus theta. And they differ here because heterozygosity is pretty large, and this is a very large value of heterozygosity. Other question? Oh, you're back, Taylor.
I'm back. My internet's really unstable. I apologize.
Yeah, welcome to the era of COVID. Yeah, I know you have no control over this. Does anybody have any questions about this? The only difference between how I did it and how Taylor did it is whether she used the approximation that heterozygosity is approximately equal to theta. I used the equilibrium heterozygosity. And those two values are the same whenever H is sufficiently small. Questions? So, did Kevin make it? He said he had a work commitment that was going to make him late.
I'm here, yes.
Okay. Do you want to give it a try for problem 9?
Sure. Let's see what if I.
Oh, yeah, the talkie problem. Yeah.
Yeah.
Put a picture and talk us through it.
Okay. Let's see. So the question was to convince yourself that each mutation results in a segregating site by drawing some coalescence, marking a random spot where the mutations occur, and then constructing a set of DNA sequences implied by those mutations. So I tried to do this twice. I'm not entirely sure if I did it right, but
so show me the base of your tree, and what was the sequence at the base?
At the base of my tree here, it was ATTGC, and I'm not sure if I have it right, but
where is now and where is back in history?
Now is here, so T4, and back in history is this 0. So I have it here.
So this is generally confused relative to how most people do coalescences.
Yeah.
The way we think about a coalescent tree, the way population geneticists think about coalescent trees is they think that the tips of it is now.
Okay.
So this is today.
It's like flipped.
Yeah. So this is often the difference between how a population geneticist and how an evolutionary biologist think about trees in a deep way. So the way a population, and therefore how they draw them, the way a population geneticist would think about a tree is this thing right here is right this second.
Okay.
You have sampled 1, 2, 3, 4, 5 sequences. This is now. And we're not going to talk about what those sequences look like yet, but we're just say this is now. At some point in the past, the way you've drawn it, these two guys had a common ancestor.
Yeah.
And this is the moment those two guys had a common ancestor.
I think
And
we can see your mouse, Dave.
you can see or cannot?
Cannot. I can see Kevin's at least.
Ah, okay. So maybe I should share my screen, which is actually not as almost as I hardly did this problem. Let me see if I can share my screen just so you can see my mouse. Let's see. Let's see. Come on. No. Sorry. Why? I'm going to learn how to get this done right every time sometime. Share screen. There it is.
Yeah, I think I got confused by how Gillespie notes it. I think it was like when I see a 0, I think beginning.
Yeah.
No.
Yeah. So exactly. So population genesis denotes time 0 is right now.
Yeah.
All other times are in the past.
Yeah.
So, and the way a population genesis would draw this coalescent, this phylogeny of, I don't know, 5, 8, 10 sequences, is this is right now. And the idea is, the way it's drawn, ignoring anything about the sequence, these two samples, these two literally alleles, had a common ancestor some time ago in the past. And these two had a common ancestor some time ago in the past. And these 3 had a common ancestor some time ago in the past. These 3 had another common ancestor. These 2 had a common ancestor there. These 4 had a common ancestor here. These 7 had a common ancestor there. And all 10 had a common ancestor here that sometimes we'll call the most recent common ancestor of all of them. Yep. And the notion is there's some sequence that was held by the most recent common ancestor. Here the sequence is a single nucleotide, because I'm a lazy guy and I stole this from somewhere, that at the most recent common ancestor, the whole sequence is one nucleotide, and that nucleotide is a G. And this is the tree. So we'd expect all the descendants of this common ancestor to have a G everywhere, unless there was a mutation. And here, in the common ancestor to these guys, this branch in the tree, there was a mutation from G to T. So the sequence that had been G in the common ancestor and was descended as G to all of its descendants, here mutated from G to T, so that all of the descendants from this point down in the tree have a T. And the way coalescent, the way we're going to model this when we do coalescent theory is we're going to separate out the process that gives us trees, the process that estimates, that models, that gives probabilities for how recently we get common ancestors, from the mutation process, which is just a Poisson distribution once we know the tree. So when doing coalescent theory, we'll think about how to create a tree, and we'll think about how to add mutations to that tree.
So correct me if I'm wrong, but the most recent common ancestor has one nucleotide, which was G.
Yep.
There was some sort of copy that, is this right when I'm assuming this? Like, you see like the 2 branches from that most recent common ancestor. There was some sort of, if you look on the left side, there's like a GG. Is there some sort of copy that went on? So like those 2 organisms have a GG sequence, correct?
So I think the way to think about it might be starting at the bottom.
Okay.
We have two sequences right here. This is my allele, and this one is your allele.
Mm-hmm.
And it turns out you and I have a common ancestor.
Mm-hmm.
We're not brothers, so our mother wasn't our common ancestor.
Yep.
We're probably not even like second cousins, so it probably isn't like our grandparent. But the way it's drawn, it was only a few generations ago that you and I had a common ancestor. So, somewhere in County Derry, like 15 generations ago, you and I shared a grandmother.
Mm-hmm.
And that grandmother is denoted by this. And she had two children. One of those children gave rise to the lineage that gave rise to me. And the other child had a lineage that gave rise to you. But that grandma in County Derry was our most recent common ancestor.
Okay.
And it turns out, you, me, and Brooke have a common ancestor in Dublin, a few generations back from that, so forth. And so when you get back here, we got sort of 10 of us. It turns out, like, for all 10 of us, it's probable that all 10 of us have some common ancestor that lived, I don't know, in Kenya. And this common ancestor that we all had that lived somewhere in Africa, one branch gave rise to the lineage that ultimately, sort of moved to Dublin. And the other lineage gave rise to the people who say moved to Asia. And, but this is two people, hanging out in Africa 150,000 years ago.
Yep. Makes sense. Okay, cool.
Does this make sense to everybody?
So the way you've drawn it, you can have coalescence like without having changes in this DNA sequence. Like
in fact,
very right-hand side.
In fact, when I model it, I'm probably not even going to allow changes at the time of the coalescent. I'm going to model it as you can have a coalescent event or a mutation, but probably not both in the same generation or at the same instant, at least.
I was gonna say it's bad time to think like a physicist because I was, the notation 0 starts at rather than is now. So
physicists never think of backward time problems. Hardly.
Yeah.
They're modeling everything almost always forward time.
Yeah.
Population geneticists model everything backward time because what matters is the history, not the future.
Yeah.
So does this make sense to everybody? And yeah. So up next is Jim with the next problem.
I don't know if I'm the best one for this, but I can set it up at least.
Set it up at least. Oh, I see. Yes. The fun one.
I can get, at least as far as the intuition of how to set it up, and then someone else will probably have to do it because I didn't get any further.
Hey man, if you set it up correctly, you have won. Because setting it up correctly is the genetics. After that, it's just a little bit of, sort of first, second year calculus. And whether or not first, second year calculus is your thing isn't what we're trying to get at here. It's whether you've understood the genetics well enough to set up a problem that is solvable. So,
okay. So the question was asking, what is the probability that two sequences will differ at exactly k nucleotides as a function of 4 and u? And so the way I was thinking about it was you can kind of think of it as two events happening at the same time. The first event is the probability that a coalescence occurs at time t. And for reasons I don't perfectly understand, but I assume somehow we can describe that as a geometric distribution. And we know the probability of that is n over n minus 1 over 4n, which in the case of n equals 2 here, it simplifies to 1 over 2n.
Yeah.
And so knowing that it's a geometric distribution, we have a PDF for that. And so that's this big whole mess here. And so that's the first half.
So I'll stop you here and let's get the intuition right. Because the intuition you've already seen and is super simple. And it is almost what I said a second ago. So if the population is size 2n, and we have picked an allele for me and we picked an allele from Kevin, the probability that allele, the probability Kevin's allele and my allele came from the same mother last generation. The probability Kevin and I are brothers and that we share a mother last generation is 1/2n. The probability we don't share a mother is 1 minus 1/2n. So with probability 1/2n, last generation, Kevin and I are brothers. With probability 1 minus 1/2n, we aren't. With probability 1 minus 1/2n, not only are we not brothers, we're not even like cousins. With probability 1/2n to the third, we're not second cousins. With probability 1/2n to the fourth, we're not third cousins or whatever. Eventually, with probability 1/2n, we will have found our common ancestor. So with probability 1 minus 1/2n to the t minus 1, we have no common ancestor for the last t generations. And with probability 1/2n, we had a common ancestor exactly in generation t. So we've started with an allele from me, we started with an allele from Kevin. The probability that they were from the same mother t generations ago, or father, the probability from the same ancestor t generations ago is the probability they weren't from the same ancestor t minus 1 generations ago, 1 minus 2n, times the probability they were in that last generation, 1/2n. And this is and the exponential is a straightforward approximation of that geometric.
I had a lot of trouble with that approximation though, so I was wondering if there's maybe like a more formal way of explaining where that comes from.
Sure. So take the log, take e to the log of the geometric. Go. Knowing that the log of 1 plus x is approximately equal to x for small values of x. This is in fact the same proof you did when you estimated the probability you had no children in next generation.
Okay, so
That's to you?
moving on to the next part.
Does that make sense to you, Kiana?
Oh, yeah, that's helpful. Thank you.
Yeah. Okay. So Jim, we now have the distribution of the time to our most common ancestor. Now, you said something a little funny. You said it was two events happening at the same time. It's really the opposite of that. It's two processes happening at the same time. One random process is the time to our common ancestor, and you've written that beautifully. You've gotten the probability that our common ancestor is some particular time t. Oh, that -1 is supposed to say minus t in your picture. It says 1/2n. That should be minus t over 2n rather than -1.
Got it, yeah.
Yep. And so one process is describing the time to the common ancestor, and the other process is once you knew that time, it's the process that makes mutations. And you've written down a Poisson distribution.
Yeah, that was mostly based on your hint here.
Yeah, but that's so do you know anything about a Poisson distribution?
Well, I know it's like a binomial with a very small probability and a lot of trials, right?
Yeah, you got it. That is your intuition for the rest of your life. Take a binomial, make the probability really, really small, make the number of trials really, really big, you get a Poisson. So here what we're imagining is the probability of a mutation any generation, tiny, 10 to the minus some tiny little number. But the number of generations since Kevin and I had a common ancestor might have been quite a while ago. Maybe not so much for Kevin and I, because maybe it was from very recently. But for many of us in this room, it might have been really many, many generations ago, hundreds, thousands of generations ago. before we had a common ancestor somewhere back in Africa. So for any generation, the chance that we get a mutation at this particular locus, not so large. The probability that it was a lot of generations ago, it might get kind of large. So we've got, you might have thought the number of mutations was binomial distributed, but we've got a probability of a very small thing times a very large number of trials. It's a Poisson. And that's your intuition for everything that looks like a rare event that might have happened a lot of ways. Questions?
I had a question about the geometric distribution section when you turn it to the exponential. I was getting e to the negative t minus 1 over 2n.
That's it. E to the minus t over 2n. Is that what you said?
No, e negative t minus 1.
So remember t is in generations. So if the difference between 1,000,000 generations ago and 1,000,000 plus 1 generations ago is nothing. So I have approximated it.
Gosh, that makes a lot of sense.
Because I don't need the sort of precision to know whether Kevin and I are 53,000th cousins or 54,000th cousins. It's
gotcha.
the same either way for this math. Other questions?
Can I share how I did this one? Because I somehow skipped at the like Poisson like distribution. So I just well yeah.
It's not letting me stop and share. I don't know why.
Oops.
On ours it stopped.
Oh, for some reason it looks like I'm still sharing to me.
I can see Young Sons. Maybe you, why don't you formally hit stop share on yours, Jim?
Yeah, it's okay. I'll figure it out.
Right, everyone's okay with the screen? Like seeing my screen? Okay, so like I read the book and there was a part saying that the probability that it was about whether the mutation or the quiescent event occurs first, and then the book said that the probability that a mutation is the first event to occur it's just relative probability of occurrence, like in here. So instead of using Poisson distribution and the expected number of the mutation, I thought that the number of nucleotide sites that two sequences differ at can be thought as the number of expected mutation events before the quiescent event of these two samples occurs. So like, so I consider a quiescent event as a success, and then the mutation event to be a failure of a Verneuil trier, and then the probability of success will be 1 minus 1 plus 4nu. Sorry, 1 minus 4nu over 1 plus 4nu, as I see from here, which is actually the opposite. And then I just plug it into the geometric distribution, which is over here, and I got the same answer from the formula.
So this proof, or this intuition at least, is due to one of my academic brothers, a guy by the name of Dick Hudson. So Dick was the first guy who formulated. So what I was having you do is prove that a Poisson random variable randomized over an exponential waiting time is a geometric distribution. That result has been known for 80, 100 years. And so when people first started writing down the probability of there being k differences, you immediately got a geometric distribution as the result. And the intuition for why the geometric distribution is the result of a Poisson distribution randomized over an exponential waiting time. That intuition is due to Dick Hudson, and it is this argument. So the way Dick thought about this problem, literally 20 years after he started doing these results, was so a Poisson process has an exponential waiting time between events. And the coalescent process has an exponential waiting time between events. So if you've taken some elementary stochastic process theory, you'll know if you have two processes going on, both of which have exponential waiting times to the next event, you can start asking questions about what is the probability you get an event in this process before or after you get an event in that process. And you can even ask, what is the probability of getting 6 events in one process before you get 1 event in the other process? And you end up with a result that is a ratio of the rate of one process to the total process weight. So the probability that you have an event in process 1 before you have an event in process 2 is the rate of process 1 divided by the total rates. And the probability you have a event in process 2 is its rate over the total rates. So the probability that you have k events in one process before you have 1 event in the other is its rate divided by total rates raised to the k times 1 minus that. That is the deep intuition for why you are going to get a geometric distribution as the answer. And the only way to know that, to see that, is you've actually have a lot of results in your pocket about exponential waiting times in competing processes. So Dick, who knows more than a little bit of elementary stochastic process theory, was able to just see that's the obvious reason you're going to get a geometric distribution out of it. You don't have to do the damn calculus. And I'm not even sure I knew John had that argument in the book. Other comments? So this is the correct answer, and that is the intuition for why that's going to be the correct answer. Does anybody want to fight through the algebra, the math? Anyone want to show me the derivation?
I can do it since I dropped out earlier on my problem.
All right, give it to us.
Hopefully I can make it through this one. Okay, so we have the integral set up as Jim described it. So basically we have the integral from 0 to infinity of the PDF of the exponential with rate parameter 1 over 2n, and the PMF of the Poisson distribution with mean to ut. Here I'm just using u instead of mu. So the first thing that we can do is we can pull out this term 1 over 2n, and then we can pull out the 1 over k factorial and add together our exponential terms here. So we have e to the negative t over 2n minus 2ut times 2ut to the k. Then we're going to do our first substitution. I just started out by letting x, defining a new variable x to be 2ut. So we have x to the k here. And then we're left with, for the first term, e to the negative t over 2n minus x. And we know that my dx dt is 2u. So we have dt is 1 over 2u dx. So I'm substituting that in for dt here. And then I'm going to pull out the 1 over 2u. So we get 1 over 4 nu here times 1 over k factorial. times the integral of e to the negative x, but we have this negative t over 2n term here. And by my definition of x, we know that is negative x over 4nu. So I'm just rewriting this term this way. So it's getting to look more like a gamma function, but we're not quite there yet. So I did another round of substitution where I'm defining a new variable z that is equal to this exponential term here. So z is equal to x times 1 over 4nu plus 1. And then I can rewrite that as, and we have our x term here. So we know that by this definition, x is equal to z divided by 1 over 4nu plus 1. So I'm substituting that into x right here, raised to the power k. This is just what I defined to be z. So we have e to the negative z. And then we can basically do a little bit more math to show that dx is equal to 1 over 4nu plus 1 times dz. And I can just pull that. So we have this 1 over 4nu plus 1 to the k times itself again. So that's to the k plus 1. So I pull that out here and we're left with the integral from 0. And the bounds don't change here for the two variable substitutions. They're still 0 to infinity. So then we have e to the negative z, z to the k plus 1 minus 1. And that is the definition for gamma function of k plus 1. Which we know is equal to k factorial. So those two cancel out. And I just substituted in theta here for 4 in u. So we have 1 over theta times 1 over theta plus 1 to the k plus 1. Rewriting this term, we have 1 over theta times theta over theta plus 1 to the k plus 1. We have a theta to the k plus 1 divided by theta, which gives us theta to the k on our numerator. Denominator is 1 plus theta to the k plus 1. I can pull out a 1 over 1 plus theta here, and we're left with theta over 1 plus theta to the k, which is g hat times h hat to the k.
Could be any prettier. Very nice. I mean, you can do it in one substitution rather than two, but I like the way you've done it in two because it's getting at, you get terms involving theta quicker the way you've done it than I would have. When I do it as one substitution, there's nothing that looks like theta, like right up until the final moment, and then it all just appears magically. Here, you have almost some intuition for why this thing's going to end up in terms of theta.
It was just how I went about it. It wasn't, there was no intuition based on it. I was just trying to get it to be a gamma function.
Yeah, you could have done it. Anyway, it's beautiful. But that is also like for those who are less sort of skilled with calculus, this is one of those things where often you get an integral and the answer is fuck no. There is just no way I'm ever going to get that integral solved. But often you can look at an integral and say, but it does look like something I can solve. And if you can change the variable in such a way that an integral that at first blush looks like never, you can, if you're lucky enough and you make intuitive enough substitutions and just follow the rules of making sure you get the change in the dx term correct. And that's just nothing more than chain rule, rote followed, that you can sometimes stumble on something that is really very easy to integrate. And there's no way to know. There's no way to guess. There's no, as far as I know. You just have to kind of see it. And if it's there for you, it's there for you. And if it's not, well, you're not going to get through that problem. Oh, well. Questions?
Can I ask a quick question on notation? Am I right in thinking that h hat is just heterozygosity at equilibrium?
Yeah.
Okay.
I put the little hats on it. Taylor put the little hats on it to remind us that is the expected heterozygosity at equilibrium, which we derived last week. Theta over 1 plus theta. G hat 1 over 1 plus theta. So this will be a natural place to stop. And if you didn't have that result of 1 over 1 plus theta and theta over 1 plus theta to the k for the next few problems, If you want to get the next few problems right, I would just start with that answer and see if the next few problems now make a lot more sense to you. If you had that result, the next few problems are more straightforward, calculus-y sort of stuff. We'll stop here, I think, and come back next week, finish this homework, and I will answer questions about homework 5. And a reminder, I will not be here next Tuesday. So we're going to race through homework 5, hopefully in a single day, next Thursday. Or it'll get pushed into homework 6 a little bit. But 5 and 6 are not long like this. And they're not as, there are some ideas in there, but I don't think they're going to be as technically challenging as this was. Questions?
I had a question. Oh, you go.
Sorry, go ahead. Well, mine, I was gonna just say I have kind of like a meandering question, so I was gonna ask it to Dave, and then I don't know if people would think it was interesting or not. So I think you should go first because mine's a bit long.
Mine has to do with the next few problems. I never took calculus, so I just Googled.
Oh my!
The mean of geometric.
That's great. Congratulations.
Variance of those. Is that fine?
Yeah, you have one.
All right, cool.
The I don't actually expect anyone to have derived the mean and variance of a geometric distribution. It's I expected everybody to look that one up. The reason I expect you to look that up is even if you're good at this, I think you probably have to both differentiate and integrate to pull off that expectation, or to have, say, a moment generating function in your pocket, which is about the same thing. If you don't know how to construct moment generating functions, there's, I don't think, a good way for, if that doesn't even mean anything to you, which it can't if you haven't had a calculus-based probability, there is no good way to derive those moments. So look it up. Look up the moments, and the third or fourth problem down is something, it asks you to find a maximum likelihood estimator. And what that is, a maximum likelihood estimator for a parameter in a distribution is the value of that parameter that makes an observed set of data most likely. So in problem 10, you have the probability of observing K mutations. And you found that probability was a simple function of theta. If I told you you observed exactly 10 mutations, you could then write down the value of theta that makes the observation, 10 mutations, most likely. And in fact, what I'm doing in that problem there is I'm asking you for an arbitrary value of, if you found K differences, what value of theta would make the observation of K differences most likely? There are other ways of constructing a maximum likelihood estimator. And there are other sort of subtle differences that are in both construction and meaning of it, but they all at some level have the meaning that they are the value of the parameter that makes the observed data most likely. They certainly can take on that meaning. So the way you would do that problem is I have a function and I'm asking, and I'm observing a value K, I'm asking what value of that parameter would make that function largest. And if you knew calculus, the answer will turn out to be you differentiate that function and set it equal to 0, the derivative equal to 0. And
that's what I did.
If that's not a meaningful set of operations for you, there's no way to do that problem. Maybe you could plot it and look where the function is maximized. That'd be like if you didn't know any calculus, yeah, that's how you do it in R. But you'd have to fix a value of k, but pretend you knew what k was, make it up, and then plot what value of theta would give you the maximum of that. And then plug another value of k in and see what that gets. And then plug another value of k in, and then sooner or later you'd probably reach the calculus result. Does this make sense? All right, you want to go with the philosophy, Linnea?
Sure. Okay. So it's just a general question about neutral theory. So in the second half of homework, we make a lot of like estimations, and those are based on mutation rates at each loci, I guess, being about equal, and those mutations themselves being independent. But last semester in evolutionary biology, we read a paper by Richard Lenski. It was a long-term evolution paper using E. coli. And what they found, I guess they were trying to see if they could get convergent evolution, but it turns out to be pretty difficult because in order to get this like very shocking result they have, which was that the E. coli adapted to use like a different energy substrate, I guess, like a different nutrient resource, if you were familiar with that. But in order to get that like very striking adaptation, they had to first have a mutation that I think seems to be effectively neutral when it first shows up, because its only purpose is that they saw was to increase the mutation rate of a different locus. And once it did that, that increased mutation rate allowed for the adaptation to occur. So I guess I'm wondering, like, is that just like a freak accident or something? Or does this happen a lot? Like mutation rates are not going to be independent of, or mutations are not independent of each other, and neither are mutation rates.
So, so that the first thing to say is mutations are very, very rare in nature. So for almost any organism, the per site mutation rate per generation per site is a small number. It's probably 10 to the minus 8th per generation. Maybe it's 10 to the minus 9th, maybe it's 10 to the minus 7th. But there's virtually no organism on Earth that the per site mutation rate isn't on the order of 10 to the minus 8th. And that's because for almost every organism on Earth, we share the basic, the same sort of biology of DNA replication. We have the same sort of enzymes, we have the same sort of DNA repair mechanisms generally. Maybe not exactly the same, but we have a lot of the same mechanisms, a lot of the same enzymes, a lot of the same just underlying machinery of replication. So, so no matter what organism you look at, if you look at it in nature, its per site mutation rate was probably on the order of 10 to the minus 8th, plus or minus a bit, either way. Now, let's imagine I go into the lab and I'm going to set up an experiment with a very large number of organisms in it. And I'm going to want to try to evolve something that is very, very unlikely to evolve. I'm going to want to do something that's maybe a lot of mutations away from the current equilibrium. The probability in one mutation might be 10 to the minus 8th. I can easily make 10 to the 8th organisms. The probability of getting my two favorite mutations is probably 10 to the minus 16th. I might be able to make 10 to the 10 to the minus 16th, 10 to the 16th organisms. The probability of getting 3 is 10 to the 24th. I don't have that. So if what I have to evolve to requires a very specific set of 1, 2, 3 mutations, I can't do it. But it also turns out that the reason I get so few mutations is because all organisms rely on many of the same underlying enzymes that sort of ensure DNA fidelity. So if I break those first, if the first thing I do is I get a mutation that breaks something about the underlying biology of DNA replication, that will dramatically increase the mutation rate. And if I start, so if I set up my experiment to find things that shouldn't happen because it's one mutation followed by another mutation, which shouldn't happen more than 1 in 10 to the 24th type events, what's going to happen if I observe it, and I don't infrequently observe it, is I first break DNA replication so that DNA replication is nowhere near as faithful. And now I get a mutation rate of 10 to the minus 4th. And now getting 5 or so of those things in a row, perfectly likely if my chemostat's big enough. So people have observed this forever. Like the first people who kind of observed this were E. coli guys. And what they observed was what they call an amber mutation. And amber, like in many experiments, they got amber. And what amber was is it was a mutation that broke stop codons, all of them. And once you no longer have stop codons working right, by God, you get a lot of protein variability. And once you have that kind of protein variability, I can start selecting in all sorts of weird and crazy ways. So the first step in these experiments was often just break something so fundamental to biology. I now have so much variation out there, I can start selecting for all kinds of crazy stuff. Does that make sense?
Okay. I see. So that initial like breaking of the biology mutation then is like nowhere near neutral. Like it's definitely going to be deleterious, you imagine, unless there's a very specific situation that it's advantages. And...
Yeah. Oh yeah.
Okay. I see.
This is something that is so disadvantaged. Like it has probability 1 of like killing you, almost, but not quite. And if I'm in a huge chemostat and I immediately select for that guy and then immediately give him 1,000 descendants, it's established. And so it happens very rarely, very rarely, that path in nature. But it is not impossible for it to happen that way. And probably something like that happened in, you guys probably know, what is that name of the organism that like uses that uses a great deal of RNA editing? What are they called? There are a few species, a few things on Earth that use dramatically different, effectively, codes than you and I do. And they do it by editing what codons mean. And surely something like that had to have evolved by first screwing up translation in some fantastical fashion, followed by a quick evolution to effects. And but that has happened in history, but not often.
Okay. Well, thank you for taking my question.
Well, that's just the reason we're doing this. Anyone else want to talk about anything?
I guess I have a fun fact to share. So the E. coli strain that Rich Lenski used was actually from Bruce Levin's lab when he was back at Brown.
Yeah.
I don't know how many people knew that.
So Richard was a student of Bruce's, wasn't he?
Lenski was a postdoc in Bruce's lab.
Postdoc, yeah. Not surprising. Bruce pioneered a lot of this, these type of artificial chemostat experiments. They were, that is one of his great contributions to science. He started as a proper population geneticist, but many years ago, he found these experimental systems were a lot of fun. by many years ago, about the time I was born. Anyway, other questions? Okay, I'll see you guys on Thursday to finish off this homework, answer early questions on homework 5. I will not see you next Tuesday, but I will see you the Thursday after that.